Okay, let's review over motion graphs. Key thing to understand with motion graphs is there's a reason that we're doing motion graphs. And basically the reason we're doing motion graphs is to look at the motion of objects. There are three things we're concerned with motion. X or delta x, either distance or displacement, velocity or speed, and also acceleration. Those are the three things we use to define motion. Now, key thing whenever you're thinking about any graph in this course, the first thing you want to do, does the slope tell us something? And does the area under the curve tell us something? The entire reason that calculus was invented was to look at graphs and how they work. So here's a shortcut way to do it. I'll show you two shortcut ways actually. So if I have an x versus t graph, and here's the shape of it, doesn't actually even matter right here to check these two, is let's go slope. Well, from the 5th grade, you remember slope is rise over run. Well, in this case, the rise is delta x, the run is t, and x over t is equal to velocity. You can also do it with units. We know it's rise over run. Well, x is going to be measured in meters, time is going to be measured in seconds. That's also velocity. Now let's do a quick check of area. It doesn't matter the shape of that. It's going to be 1/2 base times height because it's a rectangle, but it doesn't have to be. The key thing is it's going to be base times height. Well, if I put in my units, I have x times t. Turns out x times t doesn't tell us anything. Now here's a case where units may actually help you. You end up with meters times seconds. That still doesn't tell us anything. So let's take a look at another one, a velocity time graph. Now with a velocity time graph, and again I'll just put that shape on it, let's do the same thing. Slope, well, slope is going to be rise over run, which is delta v divided by t, and of course that's acceleration. You can also do it with units. It's going to be meters per second divided by seconds, which is meters per second squared, which also tells us acceleration. Now, area under the curve also will tell you something. So if we say area, well, again it's going to be base times height. Again, it's only 1/2 because it's a triangle. It could easily be a flat line. Well, the base is time. The top is velocity, or change in velocity, and turns out that that's equal to displacement. You can also do it with units. This is one, I think, where the units may actually make more sense, because if you do it with units, you're saying seconds times meters per second, leaving with meters, which is, of course, tells you displacement. These are the best types of graphs, because all three things I want to establish about motion I can get from this graph.
Harold, please call one.
Last one
Harold, please call
is
one.
acceleration versus time. Now, slope, rise over run, is delta a over t. We've never talked about changing acceleration, so that's not going to mean anything to us. Maybe if you go on in physics, you will encounter that, but we don't. Now, area under the curve is going to be a times t. Well, it turns out that that's equal to delta v. You can also do it from units. If you take meters over seconds squared times seconds, you get meters over seconds, which gives you that. So you can check them if you want to know what they are. Okay, let's look at converting graphs. If I can find the one that I drew. If I'm going to convert graphs, what I want to do is convert from one type of graph to another. So let's do this. And the key thing here is you probably want to do something like this. Now, I didn't put any numbers on this, so all I want to be able to do is sketch the shape of it. Not necessarily worried about that. Well, key thing, and it may help you to actually do this in words, what does that curve mean? Well, that curve means that your distance keeps getting bigger and bigger and bigger, so this is actually showing you acceleration. And it's a positive acceleration. So what you're going to have is something that looks like that, and that's what you're going to have there. It's a positive acceleration. We only deal with constant acceleration. which means this has to be a straight angled line or flat, one of the two. Now, when I get to this point, we're not changing our distance at all, so therefore there's no speed at all. So that's the case there. Now, when I get to this point, whoops, let's amend that a little bit. We have a thing here. That green line only goes, that part of the green line doesn't exist. It only goes to there. When I get to this point now, I have a negative slope. Okay, what I have here is a negative slope. And it's pretty big, so therefore I'm going to have something down here that's negative. Oh, I need to move that up some. Negative slope because it's that. Now, during this last interval here, I also have a negative slope, but it's not as much. Okay, that's what the complete graph looks like. Now, when I get ready to change it to acceleration time graph, I think the easiest thing is to go from this graph to this graph. And even if you had a problem where you had to go from the position time to acceleration time, I would still do a velocity time in the middle, because when I see this, I can clearly see that here I have a positive acceleration like that. During this interval, I'm not moving, so therefore I can't have, in this case, I can't have an acceleration. Now here, although I have a negative velocity, it's not changing, so it's also 0. This one's also 0. So the only place I'm actually showing acceleration is here. Now, if you remember our motion graph, that there's wiggles here. Those wiggles show you when this is happening. And that's the reason those bumps are there, but they come immediately back. Okay, let's do one with some numbers now. Okay, I have a velocity time graph there. And let's do it with words first. Okay, where's that graph going to have the highest speed? Now, the reason I said velocity time graph is you can get everything off a velocity time graph. Now, so I want to label the highest speed. Well, let's first of all understand what's happening here. My speed initially started at 0. And I went up to a speed of 40 meters per second. I stayed at 40 meters per second, then I went from 40 down to 0. So the highest speed is actually, let's call this interval A, interval B, and interval C. The max highest speed is going to be in interval B. The max highest velocity is also going to be in interval B. So that's kind of nice that both of them are the same answer. Now, your highest acceleration, well, I'm not accelerating at all here. I'm changing speed, so therefore it's between A and C. Well, the greatest acceleration turns out to be, and here's where you have to deal with the fact that this is a positive A and this is a negative A. So therefore your greatest acceleration actually going to be an A only because it's positive. The lowest acceleration is C. Now, if they just ask for the magnitude of the acceleration, then it would be C, because C has a greater slope, even though it's in a negative direction. Now, the greatest displacement, where's the object moving the farthest? Well, it turns out that that's area, so that's interval B. Okay, let me pause this for a minute. Okay, let's take a look at the math problems that you could be asked with this. For example, you could easily be asked for the acceleration during part A. Well, it's velocity time graph, so acceleration is velocity over time, which means it's slope. So if I would simply say slope is equal to, again, rise over run. Well, the rise on the graph is 0 to 40. So 0 to 40, and leave your units in, meters per second, divided by the time of 10 seconds equals 4 meters per second squared. So that's a solvable thing to do. Key thing, again, unless they're asking you what's directly on the graph, like velocity, it's either going to be slope or area. Anytime you see a graph, think about, does the slope tell me anything? Does the area tell me anything? Now, the acceleration during interval B, let me slide it down so you can look at it again. It's rise over run, and it's not rising. So therefore the slope is equal to 0. In other words, there's no acceleration. And that's what it's showing. Okay. The other thing they can ask is they can ask you for the displacement, and that's why velocity time graphs are the best. Everything you want to know about that you can find. So if you ask for the delta x during part A, what it's going to be is the area during part A. And let's just do it right on the graph so you can see it. So it's going to be 1/2 base times height squared, because it's a triangle. So it's 1/2. Your base is 10 seconds. Again, leave the units in. Your height is 40 meters per second squared. Well, that's 5. 5 times 40 is 200. And if you look at your units, it's meters over second squared times second, so it's meters. It's not meters over second squared, it's just meters over second, so therefore it's just meters. So you went 200 meters during the first interval. So therefore you could say, what is delta x? Well, obviously during A it's 200 meters. The last thing you could be asked is, what is the delta x total? And let's just completely do that on the graph. In order to do that, what you're going to have to do is split it up into areas that you can handle. You have already done this area, and you said it was 200 meters. Now split it up into this area. Let's make that line up with that. Well, that's easy. That's simply base times height, which is going to be 40 meters per second times your time of 20 seconds, 800 meters. The last one would be that, which would be 1/2 base times height. It doesn't matter that it's negative. This would have a negative slope, so it has a negative acceleration, but the displacement is still in a positive direction. The only way I would get a displacement in a negative direction on this graph is if it's under the 0 axis. So in all this displacement, you're speeding up, you're maintaining a constant speed, then you're slowing down, but you're always heading away from where you started. So 1/2 base times height, 1/2 40 meters per second times this times 5 seconds. 20 times 5, 100 meters. So your total would simply be the addition of those, which is going to be 1100 meters. Now, make sure you understand that I can have something that looks like this. I can have a velocity time graph where I can have this. Now, if I have something like this, this would be a positive delta x, but this area over here would be a negative delta x. So in this case, the object spent a little bit time going forward, but then it spent more time going backwards. So this is going to end up, if this is your starting point, let's call this interval A and this interval B. A would look like that, and then B would look like that. So your total delta x is going to end up with a negative delta x. So be prepared for that, and we'll talk more about it in class.